Good afternoon, everyone. Good afternoon, everyone. Welcome to what is the first session of our ICAM Week of Science. Before we start, let me first say that until sometime around 9 o'clock on Thursday evening, we thought we were going to have this meeting in person and in hybrid mode, but we discovered on Thursday night that the campus, UC Davis campus, was going to be closed, and so there was a rush of activity, and we've managed, thanks to the great efforts of Brittany Hong and also my co-chair Rajiv Singh, been able to convert the meeting to being entirely online. Of course, we don't like that. We would love to have been together, but we're hopeful that in some meetings soon we'll be able to all be together. So as you know, ICAM is committed to exploring the frontiers of emergent matter, be they quantum, soft, or biological. And at our meetings every year, we hold a meeting where we look at some of the new developments in each of these frontier areas. And so this afternoon, we're going to be discussing frontiers of soft and active matter. The afternoon is going to be chaired by Kanka Gadar, and I think I'll hand over to him. Thank you very much.
Okay, I guess we should start, right? So before I introduce the two speakers in this session, as I understand, and that I'm chairing, and just a little bit of rules. So we like to enforce the Fraunfelder rules, which means just for the speakers, I wanted to say that please leave 30% of the allocated time for discussions, which means you have a 45-minute slot. So if you could finish up within 30 minutes or so and leave room for questions, that'd be great. And if you'd like, I could give you a warning at the 25-minute mark, so you'd know you have 5 more minutes left. Now, this is give or take, but I'd really urge the speakers to leave some room for questions. Having said that, the first speaker today, I'm very happy to now introduce Oleg Lavrentovich, especially because he's from my institution, Kent State University. Good to see you, Oleg, again at a distance. I'm sitting here in Pittsburgh, but so we're all at the. But so Oleg is going to talk about his recent work, and without much more ado, I'll let Oleg start. Thank you very much.
Thank you. I would like to thank the organizer for making it all possible, even in this not in-person mode. I think some young scientists might join. And let me ask you, you see the screen, right?
Yeah, it looks great.
And you hear me. Wonderful. So I will present how one can use liquid crystals to control so-called active matter that for many of you is known to be extremely unstable and full of defects. So those are the main students involved in the research. Taras Turin, who recently defended his thesis, and 3 current students, Runa Koizumi, Hen Bazar, and Mostabara Jadi. And we collaborated with our colleagues at Kent State, Sergei Shayanovsky and Chiho Wei, who recently left Kent State for a permanent position in People's Republic of China. Igor Aronson at Penn State and Julia Yeomans at Oxford in the United Kingdom. So the next slide shows a picture, a video that is a source of our inspiration. What you see here is a little drop of water in which there are swimming bacteria, Bacillus subtilis. And you might see that they are very effective transformers of chemical energy of nutrients into the mechanical energy. And one might think that if somehow one could streamline the swimming activity, then maybe one can extract some useful work at the microscale And the problem is that it's very difficult to convey to the bacteria what do we want from them. Of course, one can create the gradients of nutrients, but any gradient is temporary. And in order to obtain a sustained directional motion, one needs to do something else. And this was the motivation of our work. We decided that if you will place the swimming bacteria in a friendly environment that is at the same time orientationally ordered, so a liquid crystal, then probably we could control the dynamics of this particular set of swimming bacteria, and maybe it can be expanded to other entities such as artificial microswimmers. So I will start with a brief introduction of hydrodynamics at the so-called low Reynolds number and the famous scallop theorem that limits the way by which the microorganisms could propel themselves. Then I will briefly discuss how liquid crystals are different from water, from the subject of normal hydrodynamics. And we'll discuss how life changes at low Reynolds number when it occurs not in water, but in a nematic liquid crystal. And finally, I will talk about how to use the liquid crystal environment to control individual and collective behavior of swimming bacteria. So here you see nothing else but the second Newton's law, which is also known as the Navier-Stokes equations for incompressible Newtonian fluids. And the Reynolds number is simply the ratio of the inertia term to the viscosity term. And for scales L here, and velocities that are at the scale of micrometers and micrometers per second, for typical viscosities of environment, this number is extremely small. And that means that the inertia terms can be neglected. And all we are left with is a Stokes equation, which doesn't contain time. And as was noted by Parcel, it simply means that at microscales, the swimmers must develop some activity that is not time invariant in order to propel themselves. And he presented an example with a little scallop of microscale length that could not swim if it would just open and close its mouth. And in the nature, one can find examples such as swimming bacteria that overcome this limitation and create time irreversible propulsive mode. But swimming bacteria with flagella are one example. This helicoidal appendage rotates, and since the viscous resistance to each element of the flagellum is different for the direction parallel to the flagellum and for the direction perpendicular to the flagellum, one creates the persistent propulsive force shown here with the red arrows. And this is how the bacteria propel themselves. Now, people are always interested to produce something artificial and as simple as possible in order to mimic this propulsive activity at the microscale. And here I show just two famous examples. What would be the simplest types of artificial microswimmers. One is on the right-hand side, representing three spheres that are connected by rigid rods. And these rods change their length. And as a result of time irreversible protocol, this triple sphere would propel itself. As simpler in some sense, at least in the number of spheres involved solution, is shown in the middle of the page. It's two spheres that are connected by a tube that pumps the fluid from one sphere to another. And again, you can develop a protocol that would propel this structure. forward. Of course, in both cases, you have to spend some energy. You have to provide the energy to the system in order for the system to perform work. And as compared to those two solutions, the 3 spheres and 2 spheres, I would like to argue that in a liquid crystal environment, the situation might be simpler in the sense that even a single sphere with some type of activity can propel itself. So you don't need the second or the third sphere for the propulsion to happen. And in order to understand what's the main difference between a liquid crystal and isotropic fluid, I just show you a couple of slides here. So liquid crystal of the nematic type, and this is the type that we are dealing in this presentation, is the material that is formed by typically elongated molecules that are oriented along one direction called the director. And this direction is the axis of anisotropy of all properties like dielectric, permittivity, viscous drag, birefringence, and other things. So since the ground state is a uniform alignment of the director, any attempt to create a deformation of orientational order implies some elastic resistance. And here I show the formula for the elastic energy, which is the integral over the deformed volume of the gradients of the director field. And of course, it's not just gradients, but the gradient squared, because let's say left and right-handed splay shown on the picture would be of the same energy. This is why we have a square. And if one think about the dimension here, then one would conclude that the elastic energy scales linearly with the size of the system, which is a very important conclusion, because if you now compare this bulk energy with the surface energy, which stems from anisotropic molecular interactions that cost some energy when the external pore tends to deviate the director from the direction that is preset by molecular interactions, then this energy is growing as the surface area or as the square of the typical size. So now if you compare the elastic bulk energy and the surface anchoring energy, you would realize that counterintuitively, the surface energy wins when the system is large. And large means larger than the ratio of this material parameters, elastic constant K and anchoring coefficient W. And in typical liquid crystals, this ratio is on the order of 1 micrometer plus minus 1 or 2 orders of magnitude. So it's precisely the range of many biologically relevant things like cells or bacteria, and slightly larger than viruses. So let's consider how this consideration applies to the simple object, a sphere at the surface of which the surface anchoring prefers to see the director perpendicular to the sphere. And imagine that such a sphere is dispersed in a nematic liquid crystal that otherwise is uniformly aligned. The question is, what would be the configuration of the director field around such a sphere? And of course, the answer depends on the balance of the elastic energy that scales as the radius of the sphere and the surface anchoring that scales as the surface area. And if the sphere is sufficiently large, then, as I already told you, the surface anchoring wins, and that means that the director must be perpendicular to the interface. And one of the simplest solutions is shown here. The director turns perpendicular to the interface, and if I produce some symmetric configuration, then I might end with the Saturn ring configuration. Later on, it was realized by von Lubansky and his colleagues that a simpler and energetically preferable solution might be when the Saturn ring, which is a loop defect is shrunk into a point, either on the right-hand side or left-hand side of the sphere. And then one deals with the dipolar geometry of the director configuration with the so-called hyperbolic hedgehog, in this case on the right-hand side. So you can see this hedgehog if you take a microscope and disperse the water droplet in a nematic crystal. In this video, it's on the right-hand side. And what else you can see? You can see the Brownian motion. And here I show the trajectory of the center of mass of the droplet. And you see that it's similar to a Brownian motion in an isotropic fluid, with that difference that the far field of the oriented director makes this cloud of trajectory slightly elongated along the director, along the horizontal axis. But other than that, the dynamics is similar to normal dynamics, and especially in the sense that this droplet doesn't move anywhere. If you take the integral over a long period of time, you would see that the droplet remains in the position at which you started. So the question is, imagine now that it's just not the water droplet. Imagine that inside of this droplet of water, we have some activity, some swimming bacteria. The question is, what would happen then? And the next slide shows that the situation changes dramatically. What you see here is the droplet of water with bacteria inside, and the hedgehog is on the right-hand side, and the bacteria doesn't show a Brownian motion. It shows a ballistic propulsion. If you measure the displacement as the function of time, for the horizontal direction, you would see this ever increasing path. And this is a ballistic motion. Now, it's important to realize that the symmetry of distortions of the director is of crucial importance. If, for example, one creates a sample in which the glass plates are not that far apart from each other, so that the droplet almost touches the glass plates, then it's the Saturn ring configuration that is stabilized. And as you might see here, for the Saturn ring, there is practically no displacement. It's only when the Saturn ring shrinks on the right-hand side into a point, only then you start to see some propulsion. So the symmetry of the director distortions is of prime importance for the propulsion to happen. The next slide shows that if you melt the liquid crystal, then the propulsion stops. If you destroy this orientational order, like at this moment when the temperature was 35 degrees centigrade, then the nematic melts into the isotropic phase. There is no director field, and the propulsion stops. You might observe normal Brownian motion without any displacement in this case. So the question is, what's going on? How to understand this propulsive mechanism? Here I show the video of what's going inside. So the video doesn't show you the individual bacteria, but what it does show is the fluorescent markers that are dispersed in water. And because the bacteria are swimming, the markers are moving around, and that indicates that there are some flows. If you try to find some order in those flows, you would fail, because there is no direction or no regular vortex around which these flows would evolve. It's really chaotic, and if you integrate the velocities over a long time, you would see practically isotropic distribution. But then if you do a similar analysis of the flows of the nematic fluid outside of the droplet, and this is the right-hand side of the movie, then you would see that the situation is totally different. The flow is noticeable, and in the coordinate frame that is fixed with the droplet, this flow is from right to left. And if you integrate over a long time, then you would see that this flow persists. And this is why the droplet moves. If now you let the droplet go, then it would move in the direction opposite to the flow of the surrounding nematic. How do we understand more qualitatively and quantitatively this effect? So here I show you the vertical cross-section of the cell. The droplet is in the middle, and these bars on top and bottom are the glass plates. And the glass plates want the director to be tangential to them. And the droplet, as I already said, prefers to see the director perpendicular. So the activity of bacteria inside the droplet create the flow that are transferred through the interface between the two fluids. And if this displacement is directed to the left, then the director is going to be distorted, as you see here. If it's directed to the right, then the director again needs to be distorted in a different way, because the surface anchoring keeps the director perpendicular to the surface of the sphere. And then if I compare the two configurations for the same displacement of the droplet to the left and to the right, I would see that the director configurations are totally different. In the case of motion to the right, the director is more horizontal, more uniform. And in the case of motion to the left, it's distorted. And that's the mechanism. Since the director configuration offers different viscous resistance to the flow that depends on the orientation of the director with respect to the velocity, I have different resistive force for two equal displacement. And this produces the overall motion, and one can estimate it as something being proportional to the viscosity difference for the more oriented director and less oriented director. Now, since we know the relationship between the surface anchoring and droplet activity, we can try to control the dynamics in many different ways. Here you saw one example when the liquid crystal is predesigned in such a way that it forms this radial structure. And if you put the droplet somewhere at the periphery of the structure, it will be accelerated towards the center. And then once it reaches the center, the surface anchoring at the droplet matches the pattern field, and the droplet stops. So you can design like bus stops for the dynamics of the droplet. You can also use the electric field. For example, using the pattern electrodes and realign the far field in which the droplet is located. And then you can direct the droplet to any trajectory you wish to have. Here I show an example with droplet making complete reorientation of its directionality. And using electric field, you can also control the speed, because if you increase the electric field without changing its orientation, then you can expand the Hitchcock into the Saturn ring. And Saturn ring configuration is quadrupolar and cannot move in either direction. And because of that, the droplet stops. So I would like to conclude the first part with the simple statement that if you replace the isotropic Newtonian fluid with a nematic environment, then you have the capability to enable propulsion of water droplets with some kind of activity in it. And you can use the nematic director field to control the trajectories and the speed of active droplets, either through patterning of the director or through the interaction with the electric or say magnetic field. Now, the last portion is about how can we use liquid crystal medium to control not just a bunch of bacteria inside the water droplet, but individual bacteria. And for that, of course, we again, want to streamline the motion that is shown here in isotropic fluid to something that is more ordered. And I will show you two examples. One is kind of jet motion, and another one is circular polar motion. So, of course, if we disperse individual bacteria in a liquid crystal, this liquid crystal must be friendly in the sense that it's, let's say, water-based. We cannot use the so-called thermotropic liquid crystal that we used in the first portion of the presentation, but we have to use the so-called lyotropic liquid crystal. And here I show the structure of such a lyotropic, we call it chromonic liquid crystal. So it's molecules of a disc-like shape that are dispersed in water. They have hydrophobic pores and polar peripheries. And while in water, they prefer to shield their pores from water. It's a hydrophobic effect. And they aggregate into elongated cylindrical bodies. And these bodies form a liquid crystal because through Onsager model, elongated objects at a sufficiently high concentration would prefer to align parallel to each other to decrease the orientational entropy. So we are using this material as the background in which we dispersed swimming bacteria, Bacillus subtilis. It's the same type of bacteria we dealt with before. And you might see here a swimming bacterium. It's even visible how it rotates the flagellum exactly because the medium is a liquid crystal, and that means birefringence. And the perturbations of the nematic are being visualized in polarizing microscope through the wave of dark and bright spots. So what would be important for us is to realize that this motion is force-free. In other words, whatever propulsive force the bacterium creates is being exactly compensated by the drag force. And so we can present the bacterium as an ellipsoid at the extremities of which we have two forces of opposite polarity but equal magnitude. So if we prepare a uniformly aligned chromonic nematic liquid crystal and disperse bacteria in them, we achieve some success in terms of control. You see here that the bacteria move horizontally, but it's not yet what we want, because the amount of bacteria moving to the left and to the right is the same. So we cannot extract simply some work. And it turns out that we could extract some work if we start to distort the director field. And distortions are not just any distortion. I show you the next slide in which we have two types of distortions. On the left, it's circular distortions of the director. And you see here that the bacteria move left and right, clockwise and counterclockwise with the same probability. And on the right, it's a radial distortion. And again, the number of bacteria going in and out of the center is about the same. But then surprisingly, if you mix the two types of deformations, the circular and the radial, and create a mixture, then in this configuration, you achieve a polar propulsion. I show here the bacteria that move in the vortex that is designed with this chiral asymmetry. And you might see that they move in the same direction. You can measure the velocities shown on the right-hand side. And the mechanism here is the interactions of neighboring bacteria with each other. So I show the two bacteria that are aligned by the underlying nematic background. So they are at some angle with respect to each other. And their interaction is such that the horizontal components of the forces cancel each other, but the vertical could not, and this vertical net force is directed upwards. If I move 90 degrees to the left, then I would see a similar picture. And if I repeat this thought experiment, I would realize that my hydrodynamic interaction force is circular, and that's the reason for the propulsion of bacteria in circles. I can write down the expression for this active force of hydrodynamic interactions in this vectorial form in a slightly different shape. It was written by Simha and Ramaswamy for active matter some years ago. And since I know my director field, I can find out what exactly is this force in the shown geometry. And I would realize that the radial component is 0, but the azimuthal is not 0 and goes as 1 over r, where r is the distance from the center and alpha is some activity coefficient. And then I balance it with the drag force, and I find out the velocity field that is matching the experimental field rather nicely. And at least qualitatively, I know that the reason for this collective behavior is interaction of bacteria, which are pre-aligned by the nematic environment. So the question is, okay, if the bacteria are very far away from each other, then apparently they wouldn't interact. So what does it mean to be close enough? And we did experiments, Runa mostly did, with different concentrations of bacteria. So if they're really far away from each other, they simply follow the pre-designed director field. But once their concentration increases, they start to show some elements of collective motion. At the bottom, you can see the kind of integral of this video that shows the trajectory. And finally, if the concentration exceeds some threshold, then the bacteria start to show this collective motion and gather in circles and swim in a polar fashion.
Like 5 minutes?
Yes, thank you very much. So the mechanism, again, is very similar to what I already discussed. If bacteria are far away, they don't interact. If they are close to each other in this orientational pattern, then they create the hydrodynamic forces. And if you play with the spiral angle, you can produce also kind of situations when the bacteria would gather in the center or when they would expand to the periphery. It's only 45 degrees, more or less, for which the bacteria swim in a stable circle because there is no radial component of this active force. And the experiment confirms just that. Depending on how you design the director field, you can create a condenser of bacteria, or you can clean them out of the system and push them to the periphery. And the final slide is a similar approach to create now not a circular motion, but a motion with unidirectional propulsion. So I deliberately didn't show you the director field, hoping that those who are not familiar with this work would think. Now I show you the director field. It's the periodic lattice, one-dimensional lattice of splay and band, and I show a fragment here. There are no physical walls. If you go up or down in this movie, you wouldn't see no hindrance for the motion of bacteria. It's just the curved director field that condenses the bacteria and forces them to swim unidirectionally. And for comparison, I show you where we started with the chaotic motion. And this directional propulsion allows us to force the bacteria to perform some useful work. You might argue whether it's really useful or not, but the bacteria push the colloidal particle, a polymer sphere, from left to right. And of course, you can design this trajectory to your specifics and deliver this colloid or droplet to a destination of your choosing. Okay, the final slide is that liquid crystal environment really allows you to gain some control over the active matter, and we show it with the example of swimming bacteria. We think that artificial swimmers can be similarly controlled In particular, the liquid crystal environment overcomes the limitations of the scallop theorem and enables active spheres to propel themselves, and one can use the liquid crystal environment of various types, thermotropic or lyotropic, to control the trajectories and speed of microswimmers. Thank you very much for your attention.
Thank you, Oleg, for a very nice talk. So from the audience, if you have any questions, please raise your hand. There is a reaction button and you can click on that, and there's a raise hand feature. You can also text if you don't find that. So please feel free to ask Oleg questions on his talk.
Can I ask a question? I'm on the wrong.
Josh,
camera.
please ask question. Yeah.
Hey, Oleg. Now I'm on the right camera. So can you give us a sense, are there liquid crystal environments in nature where the bacteria find themselves? I mean, is this something maybe they have evolved to do or could take advantage of, so either, you know, in a host, in a pathogenic case, or just anywhere out in the wild?
Well, it's not that the bacteria were growing in a liquid crystal environment. I don't think that Bacillus subtilis, for example, would meet the liquid crystal environment in its childhood, and then you bring it to the lab and it would perform. No, it's an artificial system. So it's the system designed to control the dynamics. Bacteria, you know, yeah, they form collective modes when they are at very high concentrations. And since they are rod-like, these high concentrations make them a liquid crystal out of themselves. So they don't need the environment to become orientationally ordered. So at high concentrations, the bacteria form, if you wish, a liquid crystal, and then they start to swim in circles with certain polarity. It's not only bacteria, sperm cells do that, and many other living organisms do that. They form liquid crystals out of themselves.
Okay, so I think Piers and then Jose.
Yeah, thank you, Oleg, for a very nice talk. Have you experimented with the effect of using cholesteric liquid crystals, something with a natural twist?
Yes, we tried, but besides some obvious results that if you create the twist, then the bacteria swimming near one plate would go this direction, let's say south-north, and near the top they would go west and east. There was nothing of interest, but I have to say that we are at the beginning of this exploration, because we expect many interesting things to happen, since the bacteria by themselves are chiral objects. And for example, a bacterium that is placed in the normal shear of co-ed cell, for example, would experience some lift because of the chirality. So we kind of plan of playing with this chirality of bacterium versus chirality of the medium.
Okay, Jose.
This was a very interesting talk, and I think it's interesting to think about the possibilities. You're commenting about the fact when the concentration increases that the bacteria create its own liquid crystal environment. Would that have any functional reason for the bacteria, how it moves, if it's a very dilute environment where we just be moving chaotically and looking for something, but when it get organized, try
yes,
to...
yes, but this is more the subject of fundamental active matter physics rather than liquid crystals. You know, the school of fish often form the nematic liquid crystal and vortices, and people say that it helps them to evade predators like sharks, because you know, when the shark is inside this circulating swarm or school of fish, it's very hard for it to target one fish to eat. So that's what they do in nature. Then many ants.
You're saying that you have the same phenomenon from bacteria to fish.
Yeah, but you know, I just give you the example.
Good example, yes.
In the case of bacteria, in which they do form swarms, I really don't know what might be the physiological reason for that. There are some tragic examples, like ants would form the circular trajectories following in traces of chemicals one after another. And they could not escape till they die. So they go in circles till you know, the nutrients expire and the ants expire. So it's an example when it might be detrimental. In the case of fish, it's probably a positive outcome.
Any other question? I'm checking to see if anybody has their hands up. So I have a question, Oleg, which is probably just a simple question. Does this concentration of in the second part of the talk, does the concentration of bacteria change anything? Does it change with how many you have?
Yes, it's a dramatic effect. Here the concentration, there are two regimes. One regime is that the bacteria are so far away from each other that these water jets that are associated with their swimming do not overlap. And then the bacteria behave as individual entities. There is no interaction. This is the case here. You see, if you put them in the oriented director of the liquid crystal environment, they follow the director. They don't listen to each other. But if the concentration is such that the distances between them are smaller than about 20 micrometers, then these jets start to overlap. And if there is a misalignment of two bacteria, then these two forces cancel horizontally, but add up along the vertical direction. And that creates the torque, and that ultimately leads to this collective motion in the circle that I show on the right-hand side. So here the concentration is 10 times higher than in the individual case. And so, yes, the concentration controls the interactions between the bacteria through hydrodynamic forces. And that leads to completely different dynamics of collective dynamics.
And so in this case, in this particular liquid crystal, they'll always spiral into a circular motion, or is there any other motion that can be generated?
Yes, if we create the vortex environment, then it's always either clockwise or counterclockwise, and we can decide which would it be, clockwise or counterclockwise, by controlling the geometry of the structure. But the environment can be designed in a different way. Here is an example. And so it's a linear propulsion because the director field is not circular, but in the form of periodic splay and bend. It's just a fragment that is shown here. So you can design whatever you want. And the important thing is that the motion is polar.
Thanks. Anybody else have any questions?
Yeah, I have another question. Hang on, I'll put my red. Yeah, so I actually have two questions. First of all, can you explain how you produce these configurations, these topological configurations of your nematics?
Yes, that was thanks to Chiho Wei, who developed the approach of plasmonic alignment. So what you do, you have a metal sheet, metal film, and you make very thin nanoslits. And then you shine light through it, and the outcoming light is polarized more or less linearly. perpendicularly to the long axis of the slit. And now you use the pattern of those nanoslits, which looks like these bars here, these little ticks.
Yes.
And you irradiate a photosensitive substrate. And the photosensitive molecules, such as azobenzene derivatives, they experience trans-cis configuration till they end up being perpendicular to the polarization of light that is acting locally at this location. And then we use this photosensitive substrate after we irradiate it with a patterned polarization field to align the liquid crystal. The liquid crystal molecules listen to the molecules of azobenzene and replicate their orientation. So.
And my other question was, you showed this force due to Ramaswamy et al. How well does that theoretical force do in describing your experiments? Have you simulated and compared?
Yeah, so Ramaswamy produced it on the symmetry argument that it's just allowed by the symmetry. But in our case, so we have the experiment. So we have this expression. We derive what this expression produces in the particular geometry of our director field. We end up with this force. Then we add the viscous drag. And here is the theoretical result. So the velocity predicted by this model is this, and the experiment is actually showing pretty close resemblance. And then this is the theoretical curve, the red, and the experimental points are just the points with error bars. And I would say that it's a reasonable agreement. So it's very hard to find exact agreement in active matter with any theory, but I think in our case, it's not that bad.
And if you increase the concentration, does it begin to break down?
Yes. It's important not to get overexcited and not to put too many bacteria, because then this kind of streamlining ability of the liquid crystal is compromised. And I don't show the movies here, but if there are too many bacteria, then this activity can overcome and they can create undulatory instability. In some cases, the bunch of bacteria would go away and the remaining would restore the stable circle and continue in a stable fashion.
Oh, fantastic. Okay, thank you.
So we should probably move on to the next talk, but let's thank Oleg again for a wonderful talk.
Yeah, thank you. Thank you very much.
So the next speaker is here.
In principle, we had scheduled a half-hour break here.
Is this after the half-hour break or?
No, in principle, it was now until 3:15.
Okay, okay, so let's have the break then.
So I think we should stick to that. Otherwise, we may lose people.
Yeah, I missed the break when I looked at the program. I see it now. Okay, so we have a break. We come back at what time do we come back?
At 3:15 Davis time.
At 3:15 Davis time, which is 6